Welcome to the undergraduate multiple group. This is our second talk of the year, and it's from Bryan Lam on an introduction to category theory. Over to you, Bryan.
Okay, so I want to begin with some motivation. So I guess the beginning motivation category theory is that you notice that there are many examples of like sort of sets with extra structure throughout mathematics. So for example, you have groups and their binary operations, you have rings and their multiple binary operations, you have vector spaces or modules with their operations. You know, you have topological spaces with topologies, all different kinds of these things, you know, Ewing groups, like compact Hausdorff topological spaces, whatever, right? So we have a bunch of different types of structures, you know, metric spaces with their metrics, you know, with graphs with vectors. So these are all examples of things that are like sets with extra structure, and so we want to somehow, and we also have notions of like structure preserving maps between them. So you have like homomorphisms between algebraic structures. If any of you know a bit of universal algebra, actually any algebraic variety is an example of a category. And so you have this notion of maps between structures which preserve their structure. So like all these are maps between structures that preserve their structures. So like isometry preserves distance. Graph homomorphisms preserve that at like nodes which are connected or vertices which are connected. Like linear maps preserve linear combinations and so on, right? So these are all maps between these things. So like these things, can you see the mouse? Okay. These are maps between these things which preserve the structure of the thing. And so this motivates us to describe or define a category. So we have some data, so we need objects in the category. So and this is the previous slide, this would be like the objects can be groups or rings or vector spaces, or so like if you don't understand like the abstract notion of vector space, just treat it like it's Rn or something. Topological spaces treat it like R with open sets or something, right? So you have all these objects, and then between them you have morphisms which preserve their structure. And so, of course, all of these are examples of categories, or else I wouldn't have stated them. But it's also much more general. So generally, all we need is the objects and the morphisms between them. And so we give like a quote unquote structure of composition. So if we're given an arrow from C to D and an arrow from G to E, then we can compose them. And in some sense, this is very intuitive, because if you have a map from a set C to a set D and a map from a set D to a set E, then you can compose them. Or you know, if you have a homomorphism, you can compose them. A continuous map, you can compose them, etc. And another important property is that the notion of identity. So for all of these types of homomorphisms, we have some sort of identity, like the identity of a group homomorphism, identity linear map, so like the identity matrix on Rn, the identity continuous map, so on and so forth. And so we want to have this notion of identity. And of course, associativity is very important, because I mean, like, it's kind of screwed without associativity, so we want that as well. And the usual notions of like endomorphism, isomorphism, and automorphism pretty easily generalized in a category. So like if you think of an endomorphism as like a homomorphism from a group into itself or a ring into itself, whatever, then an endomorphism is just an arrow from an object into itself. An isomorphism is an invertible arrow. So like if you compose it with something else, then you get the identity on both sides. And an automorphism is just an endomorphism and an isomorphism. And so in some sense, this makes sense, this agrees with our motivation. So these are all examples of categories, but of course it goes a lot further than that, because otherwise we wouldn't be studying this. So here are some other examples of not concrete categories. So for example, like any group or any monoid is really just a category. So if you have a category with one object, then and with small Hom sets, so like just ignore that. Just it means the arrow. We have like a small number of arrows in some sense. So if you have one object, then all the arrows obviously must go from that one object to another to itself, because they can't go into any other object. and you can compose them, which gives you the binary operation, right? Because we have the structured composition. Now, generally, this is not a binary operation because like these belong to different Hom sets. Like this belong to the Hom set CD, and this is belong to the Hom set DE. So like the Hom set just means all the arrows from C to D, and all the arrows from D to E. So generally, it's not a binary operation. But if you have only one object, and then all of these are arrows pointing to itself, so you can literally just compose any pair of arrows. It does give you a binary operation, and this literally just becomes the identity, usual identity for monoids, and associativity is just the usual associativity of the binary operation. And so, yeah, so this will give you a monoid, and if additionally every arrow is an isomorphism, that just means every element of your group has an inverse, and so it's a group. So it's that every monoid in every group is really a category. Sets are also categories, so hold on. We call a category discrete. Discrete when it has no arrows other than the identities, right? And then in this sense, this is just a set, right? Because like you just have a bunch of objects, but like no additional structure. So in some sense, this is a set, or it's bijective to the set of all sets, which does not exist, but for our purposes, we can pretend it exists. And so in some sense, this is just a set. So every set is a category, and this is an important example of a discrete category. And yeah, so pre-orders, partial orders, total orders, and binary relations are all also categories. So if you recall, a pre-order just has is just a binary relation, like with a set that has these two axioms only: reflexivity, i.e., like everything is related to itself, and then transitivity. So if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. So this is sort of like the binary relation that you would have seen in foundations, but without symmetry. And so, why is this a category? Oh, and by the way, pre-orders only have one arrow between any two objects. So like, there's only one arrow from A to B, at most one arrow. So it might have no arrows, it might have one arrow. And so the natural numbers give an example of, or finite ordinals, I guess I better give an example of pre-order, right? Because the reflexivity assures that you have for every object an arrow from itself into itself, which is the identity. And then transitivity assures that given any two arrows, you can compose them to obtain a third arrow. And this makes sense, right? Because in the usual sense of like, if A is literally less than or equal to B, like if there's a real numbers or natural numbers or whatever, then this makes sense. And so additionally, if we want any pair of isomorphic objects to be equal, that's a partial order because, I mean, like, so an isomorphism would just be like A less than or equal to B and B less than or equal to A, I is an arrow from A to B and an arrow from B to A. So if we want the pair of isomorphic objects to be equal, that's just saying A less than or equal to B and B less than or equal to A implies A equals B. So that would be a partial order. And then if additionally we want for every pair of objects to be either an arrow A to B or B to A, then that's a total order because it's like everything is comparable. And if instead of we require every arrow to be an isomorphism, that's a binary relation because every arrow is an isomorphism just means that A is less than or equal to B, then B is also less than or equal to A, i.e. symmetry in the usual sense. So pre-orders, partial orders, total orders, and binary relations are also categories. Now I discuss the notion of a commutative diagram. So a commutative, a commutative diagram is really just a directed graph whose vertices are objects in C, and whose directed edges are arrows in C. And there's a very deep connection, or not very deep, but like there's definitely a connection between graphs and categories. Because, well, you might know that every algebraic structure is in some sense a quotient of a free algebraic structure, and in a similar sense, every category is a quotient category of a free graph, or a free category on some graph. So, anyway, so yeah, so a diagram, a commutative diagram, a diagram generally is just a directed graph. Vertices are objects, directed edges are arrows or morphisms or whatever, and for it to commute, that means that any two paths from any vertex to any other vertex are the same. So ideally we decompose them. So for example, for this triangle to commute, we would require that both paths, well, there's only one path from A to B, so that's trivial. There's only one path from B to C, so that's trivial. And there are two paths from A to C, so to say that this diagram commutes just means that this path, G composed of F, and this path, H, are the same. Decompose them. So this commutative diagram is just another way of saying H equals G composed of F. And you might wonder why are you bothering with writing so much when you could just write H equals G composed of F? Well, I mean, it makes it a lot easier to visualize where everything is, so. Yeah, and this one would just be like, there's only one arrow from B to C, from A to B, one from B to D, so it's trivial. A to C, there's only one, and C to D, there's only one path. But from A to D, there's two paths, namely H composed of F and G composed of K. And so to say that this diagram commutes would just be to say that H composed of F is the same as K composed of G. And so some example applications of commutative diagrams. So suppose we have a binary operation on some set G, I called it G for a good reason, and an identity, and you might wonder why is the identity an arrow from and this is a set, by the way, and why is there an identity? Why is there an arrow? Why is the identity an arrow from a singleton set into the group or a set? And really the reason why is because you can't really speak generally in a general category, because here we are dealing with sets, literally sets. But in a general category, you don't have a sense of element, right? Because for example, if I go to what's an element of the natural numbers 0, 1 or 0, these are not sets with extra structure, these are literally things. So it doesn't make sense to speak of an element in a general category. So we want an arrow or a map from the singleton set to the set G, which picks out the identity element with respect to the binary operation. So in some sense, that this identity just uniquely determines the identity. And so, what would this diagram on the left be saying? Top left diagram is just another way of writing associativity. So why is this associativity? Well, you can imagine if I began with let's say some triple ABC, and then I first did the binary operation. Let's say I'll call the binary operation plus, right? So that this arrow would set it to it's gonna plus the first two things. Does this make sense? Then I keep the third thing constant. So this is gonna send it to A plus B, and then comma C, and then doing this binary operation here would just be A plus B plus C, right? And on the other path, what would it be? It would keep the first entry constant, and then the other two would add them. So it would be A comma B plus C. And then here it would send this to if you add these two, then it would be A plus B equals A plus B plus C. So this is just the usual associativity. To say that this diagram commutes is to say that these two are equal, right? So this is another way of writing associativity. And this one, what is this thing? That one is just saying that, this picks out the identity, right? So you have well, I won't write this singleton element. You know what I write? I will. So you have a G from the or maybe I'll say A from the set. You have A comma 1, and then let's call the identity the literal identity element of this set to be I. So or maybe E. So this is sent to AE. So we're doing the left triangle, by the way. So this triangle first would be so this would be first send A comma 1 to A comma E, and then where it is identity, and then sort of add them. So A plus E, and then maybe I'll do multiplication. Maybe A times E. And then, what does this isomorphism do? This is just the obvious isomorphism he projects. So this will send to A, and to say that this commutes this means that A equals A times B. Right, and so this is just the usual identity. And the other side gives the other direction, so this would be like the other triangle. The other triangle on the right, this is that because now this singleton is on the left, and so we would say that the identity, this would send 1 comma A to the identity comma A, and then compose them. And so this would be like EA, and this is still A, and so this gives the other side of the identity. And so this whole diagram commutes. That's just saying that A equals to AE, and EA equals A. And so E is identity in the usual sense. And so these two properties together make G a monoid. And yeah, so now suppose we have a map from like G cross some other set S to like S, and this is just the usual Cartesian product. And so what will this do? Well, again, this is just another way of writing, like, I mean, it's pretty clear from this that this should be like maybe a monoid action on this S. And it is, because what is the left diagram requiring? It requires a set, if we have like A, B, and like some S in the set, so like A, B are elements of G, S is an element of S. And this diagram would require us to first add like A plus B, comma S. And then this one would be like, or maybe I'll do multiplication, why not? So this would be like A, B, S, so I'll multiply the first two elements, right? This path. And then this path downwards is just the monoid action. So we'll write it like this, right? So this is like A, B, and then this, right? Whereas this one will first do like A comma BS, because this one is like keeps the first entry constant, and then does the monoid action on these two. So you get this, and then this will send it to doing the monoid action again. Will be this, and then to say that the diagram commutes is to say that these two are equal, which gives the usual compatibility for monoid actions. This is the first half of the monoid action, and the other half is just the identity. So that would just be saying, so this one, what does this do? Well, I really should have said that there's like this thing, like the singleton set here, but whatever, close enough. And so what does it say? This is that if you have like some element of the set S, and then you say to like the one or I call it E, yeah, E, comma S, sent to this tuple, and then multiply ES. Maybe you should write like 1 comma S. Yeah. So 1 comma S gets sent to E comma S, then the identity comma S, and then you multiply them by the monoid action. And then this projection just sends this to S, right? And to say that this diagram commutes is just to say that S equals ES. And so that makes this identity for the monoid action. And so the top two diagrams really say that this set G together with its binary operation and its identity give a monoid. And the bottom two diagrams really say that this H, this what I'm going to call a structure map, gives a monoid action on this S. And so you might wonder why are we going through all this trouble to like overcomplicate this? Like we already know what a monoid action is, a monoid is. Why are we going through all this? It's because it allows us to generalize the notion of a monoid and maybe a group to a general category. And also this is important because it gives a definition of a monad, right? So maybe talk for another day. And now we've seen the notion of how categories some categories are, this contains sets with extra structure, and some categories are also essentially just quote unquote sets with extra structure. Not true, because they are often too big to be specified. Not within the scope of this talk. So Yeah, so they're essentially just sets of vector structure, and so this naturally prompts us to ask the question of whether there are structure preserving maps between categories, right? So we sort of like going one level higher. We don't want just structure preserving maps between objects anymore. We want them between categories. So in some sense, this is the homomorphism of categories. And so yeah, so we need this functor f from C to D to map the data of C to those of D, right? Because like as usual, what does the homomorphism do? It maps elements of some object to another object. Or what does a linear map do? It maps stuff from like one vector space to another one, right? So, or a module. So what do we want this functor to do? We want it to map every object to another object in D. And we want it to map every arrow from f from C to D to f, which sends fc to fd. And so this lets us map data. And then additionally, it's not just enough to have any map between objects, right? Because like homomorphisms need to have structure. And so what this do is preserves identity and preserves composition. So in some sense, it preserves some essential aspects of the category. And so one important property of functors is that they carry commutative diagrams to commutative diagrams. So for example, like if we have this commutative diagram in, let's say, like the category C, so that this is like in the category C, and then F sends the category C to category D. So everything here belongs to D, and everything here belongs to C, right? And so this sort of looks like a map, except it's like you're also mapping the arrows, and if this diagram commutes, then this diagram commutes. And why is it true that a functor carries a commutative diagram to a commutative diagram? Well, generally, if you give yourself any path here, like let's say we would take the path like FH, FG, right? If this thing truly commutes, then any two paths from FB to FC must be the same. So this path must be the same as just this path. And so we would hope that this is true. If it does carry commutative diagrams to commutative diagrams, we would hope this is true. And why is this true? Well, because if you use this preservation of composition down here, what would this say? This would say that FH composes F composes G. Maybe I skipped a step there, but you can fill it in. Equals FH. Well, we would want to show that this is true. And why is this true? Because F composes H composes G equals FH. And that's just because of commutativity of this thing. And then generally you can replicate this argument with any path. Right? So you just given any path here, we break it down into a path here. So functors carry commutative diagrams to commutative diagrams. And really, any commutative diagram can be represented as a functor, which we will need in just a moment. Yeah, so a diagram is just a functor from an index category. So let's say these are lines on category C, right? This diagram lies in some category C. I want to encode this into a functor. You'll see why in a second. But just for now, just trust me that you would want to do this. And so how would you encode this as a functor? Well, you could build an index category, I, let's say, or J, I think is usually the chosen letter. And then an index category J. And then build a functor that sends, we make an index category that looks exactly like this category, but in some sense it only exists formally, I guess. So it doesn't really, these objects don't mean anything in the usual sense. These arrows don't mean anything. They're not maps or sets or anything. They exist formally. They're like an index set. The index set doesn't need to do anything. It's just there. So then this index category exists just to have the same, look the same, quote unquote, as this diagram you see. And then we take a functor from this index category to C, by like setting like fk equals c, so this, and then like fj equals b, I won't write the rest, but you get the idea. So I could let this functor do this, and then really I could obtain this commutative diagram in C as just a functor from F to C, from J to C. And so now, of course, I'm going to give some examples of functors. And of course, all inside with the world said the identity is a functor, right? That like sends every object to itself and every arrow to itself. Hopefully it's clear why that's a functor. The constant functor as well. Well, what does that mean? Constant functor, you would want to send every object. Oh, there should have been photos. Whatever. No, what happened to the photos? So there's a constant functor which sends every object to a certain object. So let's say like our category C looks like this is category C. Maybe there's an arrow here. Maybe there's an arrow here, I don't know. And then let's say the category D here with like D, E, F. Then a constant functor would just send every object to one particular element. So let's pick object E. So this constant functor would send every object in C to E. And then what would that entail? That forces us to send every arrow in C to the identity of E. So this is a functor, and this is a very important functor. So in some sense, that mirrors the idea of a constant map between sets, and if they're discrete categories, and it literally is not between sets, which I mentioned there. And so monoid group homomorphisms are also functors. So if you recall this, however monoid or a group is just a category, then functoriality really just requires you to literally preserve the identity of the monoid, because this is literally the identity of the monoid, and preserve like the binary operation, because this composition is the binary operation. And so that would mean that this is literally a monoid group homomorphism. And now again, using our previous example, maps between sets, right? So if their categories are discrete, then what does it look like? It would sort of look like this example, but like if you like removed all the arrows to make it discrete, so that there's no arrow here, there's no arrow here, there's something here, then this would literally just be like sends A to F of A, sends B to F of B, and so on. And so that's literally a map between sets in the usual sense. Monotone maps between orders, so like pre-orders, partial orders, total orders, right? Because what does functoriality require if you have partial orders, or pre-orders, or total orders, or whatever, that require that you preserve the reflexivity, and preserve the transitivity. So if, hold on, where is it? This functoriality would mean that if you have like an arrow A to B which represents the fact that A is less than or equal to B, and you have an arrow from B to C which represents the fact that B is less than or equal to C, then the functor will carry them to like FA, FB, FC, and this will carry this arrow to like an arrow, I didn't name this arrow, but this would be like, so in some sense this preserves the fact that FA will be less than or equal to FB, and FB will be less than or equal to FC, right? Which is just a monotone map. And dual space functor, yeah, so this one is contravariant. So like, if you recall, every vector space has a dual space of all the one linearness forms from the space down to the base field, so R, I guess. And why did I put like contravariant there? What does that mean? Well, because usually we would like a functor f to carry like an arrow from A to B to like an arrow from F of A to F of B, right? But a dual space functor does not do that, because if you recall, a linear map from T from B to W between vector spaces induces a dual T star from W star to V star, so it's in the opposite direction. So this is the action of star, right? So you've sort of like flipped the direction of the arrow. And so this is not a functor in the literal sense, but also it is, which I'll talk about in just a moment. But so this looks a lot like it should be a functor, and it is, but in some sense it flips the direction of the arrow, which does not matter, it's still a functor. And a Booleanization functor, so this would just send any group to like the Booleanization of it, so like quotient or the commutator subgroup, right? So like this functor will send any group to this thing, and then like obviously there's a like given any map from this group to like a G prime, let's say, that induces a map from G the Booleanization to the Booleanization in the usual sense, because you literally just do it on classes of this. What else I did? Oh yeah, free functor and forgetful functor. These two are like arguably some of the most important ones, because these two give rise to the notion of an adjunction, which is a very important notion in category theory. And so the free functor, as usual, just gives free objects that sends a set to like so we recall like a free vector space, for example. Well, every vector space is free, but let's treat it like the free module, right? So given any set S and a map from like S to S prime, let's say, then you recall the free you get like free modules. I'll call it Fs and Fs prime, these free modules, and then you get also an arrow between these three modules, right? And the forgetful functor is it's not the inverse, because even though it's going the opposite direction, so the free functor would go from like set to group, or like set to ring, set to space of vector spaces over a fixed field, okay, or modules over some commutative ring or topological space, so whatever. Even though this functor is going in this direction, and the forgetful functor, which takes a group or something and forgets its group structure, so it takes let's say like this set of like the infinite cyclic group, so like Z with addition, and then forgets the addition and just becomes Z, right? This is sort of going in the opposite direction, but it's not an inverse, but it does have some structure, so not all is lost. This is an injunction, which I won't talk about today, but there is some structure there. And so now we've seen categories, we've seen functors between categories, and now we are ambitious, we want to go one step higher. Can we get structure preserving maps between functors? And the answer is yes. So what does it mean to preserve like map between functors? Doesn't really make sense to map between functors per se, but it does make sense to map between the objects, like in the images of the functors. So like we can map, this is literally some object in D, and this is just some object in D. And so you could produce an arrow from this to this, right? And so in some sense, the natural transformation is just an arrow. So like, it'll associate the every object here, an arrow from here to here. So this looks like it's mapping the data of F to the data of G. And then we don't just want maps, we want structure preserving maps. And what does it mean to preserve structure? It means that this diagram commutes. So whenever this diagram commutes for any arrow from F from A to B, that means that sigma is a natural transformation. And then so, for example, using this example again, what would it mean for this to be a natural transformation? We would want this square, so with these two to commute, so this square will commute. Additionally, this square with F will commute. And then even more additionally, this square with H will commute. And if all of these commute, then we're good. And so this looks a lot like mapping this functor f from this functor to And well, we've seen categories, so this is like level 0 categories. And we've seen like level 1, which is like a functor. I spelled it wrong, but whatever. Level 2 is a natural transformation. One might naturally ask, can you keep going on indefinitely? The answer is yes. So in some, if you know what a CW complex is, this is a 0 cell. The categories are 0 cells. Functors are 1 cells. The natural transformations are 2 cells and so on. And so you can iterate this. And that's the basic notion of infinity category theory. Thought we were going to talk about it today. So, some examples of natural transformations. So of course, it's identity from a functor to itself. So what would that do? That would be like, if you have like this functor, maybe C prime, then it would just send this to f C prime, this to f C prime, and then this is just f. So this is the identity from the functor f to itself. And so also, if the codomain is a constant functor, what does that do? That'll be this page up here. Because what does it mean to so this is a constant functor with value a, and so this natural transformation will just associate every fc between our sigma c to a. And that would give us a natural transformation from this to this, and we call this a code. And it's important because we'll use it again later. And maps between images. So if you go back here, and if you imagine that, once again, if I deleted everything here, no arrows, it's just discrete. Then what does this look like? It's literally just a map between the elements of the image of F to the image of G. And so this is just a map between sets and mutual sets, where the images of G and F and G. Maybe some more non-trivial ones. So, or like more concrete ones, I guess. Projection, again, from the identity to the abelianization pointer. So, if you recall, a couple of slides ago, I talked about how this is pointer. Then this projection will just take a group. This is just a projection map from the group to this quotient group, right, to the abelianization. So this gives some natural transformation because we have for every group an arrow from that group into the abelianization. And additionally, the determinant is another example of a natural transformation. So the determinant in the usual sense, this is for a general commutative ring R or RK, but you can replace it with R if you like. So GL and R in particular just consist of all n by n invertible matrices with real entries, and then this takes a determinant, and then this thing takes it to like GL and something else. So this will take like a matrix. I'll do like a 2 by 2 matrix because it's easy. This would take like X, Y, Z, I don't think this through, Z prime. And then send this to like Fx, Fy, Fz, and Fc prime. And then you take the determinant of this thing. So you determine this thing. Whereas this path would do like, it would first be the determinant of this thing, which produces an invertible element of K. So in the group of units of K, take that and then send it to. So this takes the determinant of this matrix, and then this would take F of the determinant of the matrix. And so somehow these two are the same thing, which should be clear if you know what a determinant is. So, okay, so duality. Wait, how much time is gone by?
15 minutes.
Oh, okay. maybe I'll skip this one because it's not really strictly speaking necessary. But okay, I'll give it a basic idea of duality. So duality is the notion that really it doesn't matter whether the arrow is from A to B or from B to A. Because in the usual sense, if you have a function or a map from a set A to set B, you would say that there's an arrow from A to B. But like, that's kind of an arbitrary choice because why would it have to be from A to B and not B to A? That's arbitrary. You know, our decision of whether it's from A to B or from B to A shouldn't matter. And indeed it does not matter because there's a dual category. And so basically the idea of duality is that you reverse the direction of every arrow. And what would that look like? As in pictures. If you have like this, so this is the pre-order, and then you would reverse the arrow, the direction of every arrow. And of course it does not matter, like for example, if here you would say that like A is less than B means there's an arrow from A to B. But there's no canonical choice of whether it should be from an arrow from A to B or from B to A. Right, so this is just as valid. And so the idea of duality is that you're reversing every arrow. And in some sense, reversing the arrow does not change whether a statement is true. Right, so I want to talk about why it's true. So now, colimits and universal properties. So we this is not obviously not the analysis limit, but like some examples that you might have seen before. So probably the simplest example of a limit or a colimit is a terminal or initial object. So what does it mean for an object to be terminal? If the object A is terminal, and that means that to every object in this category, we have a morphism from this object to this category we have an arrow from every object in the category to this particular terminal object. And so what's an example of terminal object? For example, like this singleton set, this containing one element. Why is it terminal? Because there's exactly one arrow, there's one map from any set to the singleton set. And similarly, there's exactly one morphism from any group into the trivial group, where there's exactly one arrow from like the trivial any ring to it. Well, not that one, but you get the idea. So you want an arrow from any object into that thing, and then initial object is just the opposite, right? So you want an arrow from that object to any other object. And so what are some examples? Again, the trivial group, but also, in fact, because I told you before that the singleton set is an initial object in the category of sets, but it's not a terminal object, because there's no it's a terminal object but not an initial object, because there's no unique arrow from a singleton set to any other set, because you can send it to multiple different things. And so what would actually be the initial object is the empty set, because there is by definition exactly one arrow from the empty set to any other set. And additionally, some other examples, the universal arrow I guess is like one step up, slightly less trivial. So this initial arrow would just be like this. There's an arrow from A to B, and then given any other, given any like arrow from B to C, then you get a unique arrow here, such that this triangle commutes. And similarly, in the other direction, because duality, if you give an arrow from here to here, and an arrow from here to here, you get a unique arrow here, such that the diagram commutes. And kernels and co-kernels, you might be familiar with like the kernel of a linear map or something. So, well, this is slightly different from the usual notion of a kernel that you might see, but really this could just be, so, well, this is a co-equalizer, not a kernel, but it's really the same, or not the same thing, but sometimes it is, sometimes it isn't. But, so this co-equalizer would just that we would require FH equals GH, because this thing would commute. And additionally, given any arrow from here to here, we would want a unique arrow from here to here such that this commutes. And similarly, if you reverse the direction of every arrow, then you would need hf equals hg, and given any k such that kf equals kg, given any arrow. So in some sense, this is the best way to factor through. And why does this give the usual notion of a kernel? Well, this is the equalizer, but the kernel is just the equalizer with the zero map. So why is that true? Well, if G is the zero map, then what does it say? This is that fh equals 0. And so in some and if this is the usual notion of a kernel of the linear map f, right? Then, and this is the injection, so this is the alright or iota for the injection. If this is the injection, this is the kernel, and this is just saying that everything in the kernel gets set to 0, which is the usual notion of the kernel. But this only says that this only requires that everything in here gets set to 0. So it could be smaller than the kernel, but it can't be because of this property. So the universal, so this property ensures that it's smaller than the kernel, contained in the kernel, and then this property ensures that it literally is the kernel. So in some sense, it's like a least upper bound or a greatest upper bound, like a supremum or an infimum, and then literally is universologists are infimums and supremums. And so another example you're probably familiar with, co-products and products. So this could be like a product of sets, like Cartesian product of sets. It could be the usual product of groups or something. I did this in a binary case, but you could easily generalize this to an n-array case. And what does it mean for this to be a product? Well, given this should be a P projection. It's not bad. So you have projection from the product. Let's say this is like a Cartesian product of sets. Projection made it be. This projection would maybe I'll draw in the same shape. This takes A comma B, and maybe I'll use a different letter. I'll use alpha and beta because I already used A and B. And this would send this to alpha, and this to beta, right? And then, additionally, for any other object, you have an arrow. Let's say this is like some other group or some other set or something. And then you have a way of mapping that into this, or sorry, you have a way of mapping this into this. So FA here and FB. Then you get a unique map here, which is just FA, comma FB, right? So this is then FA. This is then S to FA of S and FB of S. So you have a unique way of mapping this set into this Cartesian product. And the co-products did this joint union for sets, the usual product for groups, and so on. So these are all hopefully familiar notions, but now we seek to give some unifying properties. So we want to unify all these things. We want to say how they behave the same. And so, very roughly speaking, naively speaking, we have a bunch of things. So, what's a bunch of things here? There's nothing. This is that's why it's the most trivial thing. There's nothing here. Oh, oops. Yeah. So, what's a bunch of things here? There's nothing. What's a bunch of things here? There's just the arrow B. What's a bunch of things here? It's A and B, and the arrows between A and B. And what's a bunch of things here? It's A and B, but there's no arrows between them. And additionally, we want from the universal the co-universal object. So this is the universal. This is the universal. This is the universal. This is the universal. You want arrows from to the bunch of objects, and so you want these to compute with everything else. And so in this case, there's no other objects, so we don't require any commutativity, except for this one and this one. There's no commutativity because there's literally nothing there. This one, there's no arrow, so we don't require anything else. But this one, commutativity just means that HF equals GH, or FH equals FG, which is what I wrote. And so a diagram is just it's a verbose description, but I'll cut that out because I think we're running out of time. But essentially what you're doing is we want the usual Cartesian product of sets. Then you take a functor, which encodes a diagram, which is why I said that functors encoding diagrams is important. You take a functor encoding that diagram, and then the universal object having projections. V-shape projections. So this is exactly just what I wrote before. If you have projections, then this is then like A, B to B, and A, B to A. Right? So we have that structure there, and then the unit, and then given any other cone. So I should have used capital letters, it's my bad. Then given any map, like which FA to this thing and FB to this thing, we have a unique arrow here, which is just FA of S, FB of S, such that this thing commutes. And why is the unique arrow such that this thing commutes? Well, if you project this thing, it will be FB of S, which would agree with this. And if you project this thing, then this is just FA of S, and so this commutes. And the uniqueness is because the commutativity of this thing requires this entry to be this thing. And commutativity of the left triangle requires that the left entry is this thing. And so similarly for the co-kernel for variety, the co-kernel is slightly more complicated because this time we actually do have arrows. So again, we encode this by a functor. So we encode the commutative diagram by a functor. And then we take a cone from this functor to C. So this is FJ prime. And then we have, so in some sense this is sigma J, and this is sigma J prime. And so this is a cone from F to this constant pointer. And you'll notice that there's an extra H prime here. And my original picture of the co-kernel did not have an extra H prime. Why is that? Well, if this thing commutes, then I'm just saying that H prime equals HF, but it also equals HG. And so this requires that this is the same as requiring that HF equals HG. So with that knowledge, that it's implicitly there as a composite, we can remove it and just get this. And then now, given any other arrow from this to this, universal property gives us a unique arrow, such that everything commutes. And so finally we have some example applications of colimits or limits. So the usual supremum. This could be real numbers or anything, any like lattice, let's say. The supremum will give you so like the supremum is by definition bigger than B and bigger than A, right? So these arrows exist by definition, and this makes this an upper bound. So a cone from this to this is exactly an upper bound. And then the supremum is the least upper bound. So given any other upper bound, so u is bigger than b and u is bigger than a, then it will also be greater than or equal to the supremum. So this is the least upper bound. So this is an upper bound. This is the least upper bound. This is an upper bound. And then because this is the least upper bound and this is an upper bound, this must be bigger. And dually, the infimum is similarly an example because by definition this is bigger than infimum, this is bigger than infimum, and then given any other lower bound, this is the greatest lower bound, so this must be greater than this one. So these two examples are dual. And you'll notice that it's the same thing, but with all the arrows in the other direction. Some more useful applications, I guess, of colimits or limits. So this one is to construct the p-adic as a limit, the p-adic linear field. And so these are just the usual quotient things. This is the quotient, this is the quotient. And then you have a projection. And then you have projections from this limit. And what does this look like? Well, this is just integers, mod p to the 1, mod p to the 2, mod p to the 3, etc. And so what does this thing look like? It's just like an infinite tuple of numbers, let's say like n1, n2, so on. And then how do you add them when they're ring? You add them component-wise, so let's get n prime 1, n prime 2, and so on. Add these tuples. And multiplication, same thing. And so this projection, this projects from here. This projection pi 1 returns to n1, pi 2 returns to n2, and so on. And then the fact that this commutes just means that these are the same mod p. And then another example, so formal power series, take this to be like in R or something. I take it to be in a general commutative ring K, but this could be like R if you want something more concrete, not really, but whatever. So this is the equation thing that everything by the ideal generated by x to 3, quotient by the ideal generated by x to 2, so on and so forth. What does this look like? Given a polynomial, this polynomial, so this is form of power series. And so, given a polynomial, I said like 1 plus 2x squared plus I x. Maybe I'll do it like this. This just means, well, in this polynomial, in this quotient ring, just means that you don't care about anything else here, because this is all in the ideal. Everything here is in the ideal, say quotient it out. All we care about is the constant. And then, in this one, everything about power 2 is an ideal, so we don't care about everything here, so we only care about, it's just linear. And so on, so this one, everything about power 3, you don't care about squishing it out, so we don't care about this part, and so on. And then this, space of formal power series projects into here by taking literally just quotienting it, and this is just quotienting it, and so on. So there are projections from the ring of formal power series to these quotient rings. And finally, the CW complex or CW complexes are colimits of their skeleton. So this is this 0 skeleton, so just the 0 cells. This is the 1 skeleton, so just 1 cells and 0 cells, 2 skeleton, and so on. Each of these is an injection of the like 1 skeleton to 2 skeleton, 2 skeleton to 3 skeleton, and so on. Then there's an injection from the n skeleton into the CW complex, and all these will commute. So yeah, that's all I had. Thank you.